Welcome back, everybody. So we want to take a look at the test statistic for two proportions. So the structure is as before, it's a Z distribution, and in the numerator, we have a difference. And the first part is going to be the difference of the two sample proportions. So that will be, of course, P1 hat minus P2 hat. And we're going to subtract from it the difference of the population proportions. And I wanted to point out that a typical way of setting up a hypothesis test here would be that the null hypothesis would be that the two population proportions are equal, and then the alternative is one is greater or less than the other. But since the null hypothesis is that P1 is equal to P2, that's going to imply that P1 minus P2 is going to equal 0. And so that's going to simplify our calculations somewhat. So that's what is meant right here, where P1 minus P2 is 0, assumed in the null hypothesis. The other thing I wanted to point out was that from section 8.3, where we were looking at just proportions for a single sample, the Z statistic was P hat minus P. And so here we basically have a difference of P hats minus a difference of P's. And then down below, this square root part is more complicated. So let's try to break that down some. So remember that the P bar and Q bar refer to the pooled sample proportion. So P bar is the sum of the X1s over the sum of X1 and X2 over N1 plus N2. And Q bar is 1 minus that. And so that's the numerator of the two fractions underneath that square root. And then the denominators are the two sample sizes. If you factor out the P bar, Q bar, you get 1 over N1 plus 1 over N2. And that might be easier to work with typing it into a calculator so that you don't have to type the P bar, Q bar part twice. Okay. So there's that. You can get p-values if you want to use a p-value approach. You can get that using technology. Critical values come off of our standard normal table. So that is going to be pretty familiar. The second page of this involves confidence intervals. We'll save talking about that until we get to it. So in the meantime, let's see if we can try doing an example. So the story here says a study was conducted to determine the proportion of people who dream in black and white instead of color. Among 306 people over the age of 55, 68 dream in black and white. And among 298 people under the age of 25, 13 dream in black and white. And then they give a source. We want to use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for people under 25. So our first task is to set up the hypotheses. So let's do that. So I'm going to decide that the first population is going to be the over 55 people, because they're mentioned first. And then the second population will be the under 25 people. Okay, so there's our two populations. So the null hypothesis would be that the two population proportions are going to be equal to each other. The alternative, which is the claim, is that the proportion of people over 55 is greater, who dream in black and white, is greater than the proportion for the under 25 people. So that is that P1 is bigger than P2. Okay, so then the next thing that we're going to want to do is we're going to want the test statistic. As part of the test statistic, we're going to need our pooled, our P bar and our Q bar. So let's start by getting that along with everything else. So the total people, over 55, there were 306 people. And then the under 25 was 298 people. And 68 of the older group dreamt in black and white, and 13 of the younger group, dreamt in black and white. So this will give us our P bar, and then our Q bar will be 1 minus P bar. Okay, so let me give you decimals for that. All right, so I've gotten P bar, that works out to be about 0.13411, and then its complement 0.86589. While we're at it, I went ahead and calculated the P1 hat, that was about 0.2222, and P2 hat is 0.0436 approximately. So then the next thing to do, I like to make a little sketch showing what it is that we're trying to say or test. So our test is right-tailed. So I'm going to show the right tail here. And then we wanted to use a 0.01 significance level. Okay, and so we're going to need to get our critical value for that. So let's go ahead and do that. Let me look that up. All right, so looking at our Z table, we ended up with a critical value of 2.33. So then what's left to do is calculate our test statistic and compare it to that 2.33. So let's go ahead and write down our test statistic. And this is going to be the part where we're doing basically most of the work. So it's a good idea, especially if you're just starting out, to go ahead and write down the formula as you are using it. So it was P1 hat minus P2 hat as the first part. And then in the back, I know it's going to be 0 anyways, but we'll write P1 minus P2, just so that we can kind of fit the format. And then I'm going to factor out the 1 over P bar Q bar, or the P bar Q bar, so that we're left with 1 over N1 plus 1 over N2. Okay, so I like to write out the formula like that because it helps make sure that I put the right things in the right places. Okay, so up top we need first the difference of the P1 and P2 hats. So that's a bunch of 2's, 0.0436. And then I'm going to put in the back the 0 minus, or the 0, just so that we all know that I didn't forget anything. Okay, down below we'll have P bar Q bar, 0.13411, 0.86589, and then that's multiplied by the reciprocals of the two sample sizes, which were 306 and 298. Okay, so this is going to be probably our most complicated test statistic we're going to have, if that makes you feel any better. So we just need to run this through the calculator and see what we get. All right, so going through the calculations, I ended up with 6.43, which is a humongous z-score. So that definitely is convincing that we should reject our null hypothesis. It's way in our rejection region. So we can write out reject the null hypothesis. And then our null hypothesis was that the two proportions are equal. So, and our alternative was that the over 55 group was larger. And it looks like there's evidence to support that. So we could write that out. There's evidence, let's say sufficient evidence to support the claim that the older group has a greater proportion, let's say, who dreams in black and white. Okay, all right, so that will do it. So you can see that basically we followed the kind of typical hypothesis test structure that we'd had before. What's new about it is basically the ingredients that go in our test statistic, that P bar and Q bar, and then now we have two sample proportions. So we have a P1 hat and a P2 hat. As far as the decision-making process, that part is going to be the same. But that takes us to the end here of our first example. All right, so what we're going to do next, I wanted to show you how you can do that hypothesis test for the two proportions inside of StatCrunch. So I've started up StatCrunch, and then we want to get to where we need to go. So you want to go to Stat, and then move my stuff out of the way. Stat, and then Proportion Stats, and then To Sample. So Stat, Proportion Stats, To Sample. And then, sorry, it went away from me. Stat, proportion stats, To sample. It's not listening to me today. Okay, that's because I click away too fast. Stat, proportion stats, To sample, and then with summary. That was the other piece that I was missing. All right, so then for this, you're given two things that you need to enter. The first sample, you need the number of successes out of the number of observations. So that was our first population was the older group. So we had 68 out of 306. 68 dreamt in black and white out of 306 sampled. And then in sample 2, it was 13 who dreamt in black and white out of 298. And then we could do a hypothesis test or confidence interval. We haven't done a confidence interval yet, so we'll skip over that. Let's just do a hypothesis test, and it's going to be, the null is again that the difference of the two proportions is 0. And then here, if P1 is bigger than P2, which is what we wrote, then P1 minus P2 is greater than 0. So StatCrunch here is a little funny. They show these compared to 0, and so you just have to kind of make that translation. If P1 is bigger than P2, then P1 minus P2 will be a positive number. Okay, and so you can get an optional p-value plot or bar value plot of proportions. I'm going to skip that. We'll just do the hypothesis test. Okay, so this is what you get. We got a z statistic of 6.439, which is roughly consistent with what we got by hand. And then, of course, a really tiny p-value. So those make sense. So that's how you do the two sample proportion test in StatCrunch. Once again, how to get there: stat, then proportion stats, To sample, and then with summary or data if you have data. We had summary here, so that's what we did. Okay, so that takes us to the end of our example done on StatCrunch. So that takes us to the end of this example. In the next video, we'll do another example involving a hypothesis test for two proportions, and then we'll also rework that same example doing a confidence interval. So make sure to take a look for that. And in the meantime, let me know if you have any questions, and have a great day.